Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. Today I thought I would go ahead and work through a 2-star fix with a sextant. Now, MC2 provided me with some actual sextant readings from a voyage from the west coast of the United States to Hawaii back in July of 1982. And this was a sextant training manual. And one of the things that he had was all of his sextant log readings and sextant sites along the trip. And then he would work through them. So it's a great example of how navigation is done using manual means. Now, previously we've looked at the sextant, and as you know, I've done a number of readings with a sextant, including noon sights. Now, noon sights are actually quite simple. On a noon sight, the sun is due south of your location, and all you're really determining is the latitude. Well, if you don't know your latitude and longitude, other than a basic dead reckoning position somewhere near the Hawaiian Islands perhaps, you have a way of doing something called a 3 or a 2-star fix, where you use a process called trilateration to find your location on the Earth. Now let's go ahead and cue up the music, and we'll go through this process with an actual sextant reading from a real voyage. Now, the first thing that I want to do is I want to explain a couple of terms with navigation. All right. I have here a globe because in order to do celestial navigation, you got to have a globe. Now, right here is the United Kingdom. And if you look at Greenwich in the United Kingdom, there is a meridian that passes through the globe at Greenwich, and that's called the prime meridian. As it continues down through the South Pole, it comes up on the other side and goes through what's called the international dateline, which is longitude 180 degrees. That forms a great circle around the Earth through the prime meridian and the dateline. When we look at objects up in the sky, we look for something called the geographic position of a star. The geographic position of the star has two parts to it. First of all, over what meridian is the star at zenith? And second of all, at what specific latitude is the star at your zenith, which is 90 degrees above your head? Well, in order to discover that, what we need to do is we need to go to something called a nautical almanac. And it's going to give us two values that we need to know. The first one is the Greenwich hour angle to Aries. And the second is called the sidereal hour angle of the star. Now, Aries is the prime meridian of the celestial sphere, and it is defined as the meridian on the Earth where the sun is directly at zenith at the equator on the vernal equinox in March. Now, if the center of my Gleason map was the point in the celestial sphere where the March equinox falls, or Aries they call it, that stays fixed. The Earth rotates from west to east underneath it. And at any time, we can tell the angle between the prime meridian going through Greenwich and where Aries is. And that's called the Greenwich hour angle to Aries. Now, that changes as the day goes on because the Earth rotates. Now, in addition to that, we have something called the sidereal hour angle to the star. So, starting at the center of my Gleason map, which is Aries, say we're going to go over until you see the reflection of that microphone in the mirror there. And there's an angle formed from the center of my Gleason map to where that reflection is. That's the sidereal angle of the star in reference to Aries. So you see we have two things. First of all, at any hour, minute, or second of the day, there's going to be a Greenwich hour angle between the prime meridian and where Aries is. We will add to that the angle from Aries to our star to find the longitude of the geographic position at that moment of that star. Let me show you on the software that we use for this. Now here we have an actual sextant reading from July 21st, 1982, from this voyage of this sailing vessel. Now, our estimated position is going to be latitude 22 north and longitude 155 west. And we see that on our first star, which is Capella, we have a time of 7:55:12 a.m., which is local time 7 hours off of Greenwich. And the sextant reading is that our star is 28 degrees 50.2 minutes. So what does that mean? Well, let's go ahead and have a look at the software that I use to help me with this. Now, this is an app for my iPad called Celestial Navigation. I'll put a link to it in the description. Now you see under my assumed position, I've put in 22 degrees north and 155 degrees west, and that's going to put me in the vicinity of the Hawaiian Islands. I've entered my course of 242 degrees and my speed of 7.6 knots, and I've selected the star Capella. Then I put in the date in Greenwich Mean Time. Now, 7:55 a.m., 7 hours off of Greenwich Mean Time, is going to be 14:55 and 12 seconds in GMT. So that's what we want to use. We want to keep everything in GMT just to make things easier. Now, I've put in my sextant altitude. And let's see, that's going to be 28 degrees. And it's going to be 50.2 minutes. And then I'm going to hit calculate, and I'm going to get all these numbers in here. We're not going to use all of these numbers. But the first thing that you'll see is that I've got my assumed position, 22 north, 155 west. That's fine. Now you'll see a thing called the vernal equinox, and that is the Greenwich hour to Aries. You see the little symbol there for Aries. And that says that the Greenwich hour angle to Aries is 162 degrees, 50.8 minutes. Okay, so we're going to start off with that. Now what we need to do is we need to add the sidereal hour angle to Capella, our star of interest. And the sidereal hour angle of Capella is listed as 281 degrees, 9.7 minutes. And that is from Aries. So what we do is we add our Greenwich hour angle to Aries plus our sidereal hour angle from Aries to Capella. That'll give us the meridian where Capella is at zenith. Now, as you can see, that adds up to more than 360 degrees. So what it's doing is it goes completely around the Earth in 360 degrees, and then it goes an additional amount to get up to 440. Well, we're only interested in the angle from Greenwich to the geographic meridian of the star. So what we'll do is we'll take 444 and we'll subtract 360 from it, and we'll get our longitude from Greenwich. And you can see that down here where it says Greenwich hour angle, 84 degrees, 0.5 minutes, and that's west. So that's the longitude of our geographic position of the star. Now to find the latitude of the star, we need to look for something called the declination, and it's right on this page as well. The declination is listed as 45 degrees, 58.7 minutes. So let's go over to Google Earth, and we're going to mark the geographic position of Capella. Now I've gone ahead and marked it. There's the position. It's actually in my home state of Michigan, but we'll see that in a moment. Now this is obviously in Google Earth. What I'm going to do is I'm going to use the ruler tool, and I'm going to set it to nautical miles and a circle. And I'm going to draw a circle around that spot. So let's go ahead and do that. So we'll come up here, we'll go to Tools, we'll hit Ruler. We're in nautical miles. We're going to create a circle, and we're going to center it right there at that spot. Now, how big of a circle do we draw? Well, the sextant reading from our position is 28 degrees, 50.2 minutes. Now, if we were at that point, Capella would be directly over us at 90 degrees. For every degree that we move off of 90 degrees, we move 60 miles away. So 28 degrees, 52 minutes. We subtract that from 90 degrees, and we have 61 degrees, 1.63 minutes. So what we'll do is we'll multiply that by 60 nautical miles, and it comes to 3,669.8. And we're going to make that circle 3,669.8 miles in diameter, or in radius, I should say. So let's bring this out. 3,669. All right, there's 3,670. That's actually pretty close. All right, that's within a mile or so. So let's go ahead and leave it at that. Okay, so here's our circle of equal altitude for Capella. Now, as you see, everything on that circle is the same distance away from the GP of the star, which was right about here. And at every point along that circle, if we were to take a sextant reading at that exact time, we would get the exact same reading, 28 degrees, 50.2 minutes. Now, of note, there are the Hawaiian Islands. As you see, our circle of equal altitude passes near the Hawaiian Islands. So that's an area of interest to me. Now what we want to do is we want to get a second star, and we want to draw a second circle of equal altitude. Now with two circles, they will cross paths in two different locations. One will be near what's called our dead reckoning position, which is near the Hawaiian Islands. The other will not be near our dead reckoning position, and we can discard it. We can also do it with three circles of equal altitude, and where all three circles cross, and that will be only one point, will be our position. But let's go on to the next star. So let's go ahead and pull that up. Our second star is Vega, and it is at 10 degrees, 56.1 minutes, and it was taken at 8:15:22, which would be 15:15:22 GMT. So let's go ahead and add that into our software. Let's go ahead and hit calculate here real quick. So what do we have? Once again, our assumed position is the same, 22 north, 155 west. Our sidereal hour angle is 80 degrees, 54.5 minutes. And our angle to Aries is going to be 167 degrees, 54.1 minutes. Again, if we go down to the Greenwich hour angle, that's going to come up to 248 degrees, 46.6 minutes. Now, the interesting difference between Greenwich hour angle and longitude and latitude is longitude goes up to 180 degrees. You have a west longitude and you have an east longitude. They both go up to 180 degrees and meet at the international dateline. The Greenwich hour angle starts at Greenwich, England at the prime meridian and works all the way around the Earth, 360 degrees back to Greenwich. So 248 degrees, in order for that to be useful, we have to subtract 180 degrees from it, because that answer is going to put us into the Eastern Hemisphere. All right, so once we've subtracted 180 degrees from that, the longitude in the Eastern Hemisphere starts in Greenwich, England, and works its way east. So what we have to do is we have to take 180 degrees, and we have to subtract the balance of this Greenwich hour angle from it. So let me show you what we're doing here. We're going to take 180 degrees and subtract 68.81 degrees, and we're going to come up with a final answer of longitude 111.19 east. So that's going to be the longitude. Once again, we'll look at the declination of the star, and we've got 38 degrees, 46.1 minutes. So that's our latitude. Okay, so here's the geographic position of Vega at that time and date. Now, once again, we're going to use our circle tool. And how big is our circle going to be? Well, our sight reading is 10 degrees, 56.1 minutes. We subtract that from 90 degrees and multiply it by 60 nautical miles, and that's 4743.9 nautical miles. That's the size of our circle. Let's go ahead and do that. And it's going to be a big old circle. So let's bring it out here a bit. 4743.9. That's pretty doggone close. That's within half a mile of it. So let's go ahead and save that one. And that's the Vega circle of equal altitude. That should be our position where the two lines intersect, because the other one, that's near the Hawaiian Islands. Now there's another one over here by Spain, but that's not near the Hawaiian Islands. So that we can rule out. We're going to come right back over here. And there we go. So let's zoom in on that a little bit. So that should be our position. Now, the actual position of the vessel is right here. I don't think we did too badly. Now, how much of an error do we have? Let's have a look. So we'll use our circle tool again. We'll go to our calculated position, and we'll find out how far it is to the middle of that circle. That's 4.64 miles. That's nothing to be ashamed of. The reason that I did this is that I wanted to show you that this is a relatively easy thing to do on Google Earth. You have to have a globe in order to make this work. You can't do this on any sort of a flat map. You certainly can't do it on a Gleason map or a Mercator or any other projection. It only works on a spherical object. Because as you can see, this is how circles of equal altitude work. You notice that these are circles on the curved surface of the Earth. They're what they call circles of equal altitude, which is like a great circle, but it's less than the full circumference of the sphere. Now, I gave this challenge to Nathan Oakley and Quantum Eraser and that whole crew of new sextant experts that believe that somehow the sextant proves the flat Earth. Well, it doesn't. Only one of them had the audacity to try and solve this navigation problem. They got a location right here in the Sea of Cortez off the west coast of Mexico. They were 27, nearly 2,800 miles off. My reading is on the order of 5 miles off. So I think that we've established who's the sextant expert. And as the sextant expert, there are two things that you require to use a sextant and celestial navigation. You've got to have a sphere, and you've got to have parallel rays of light. And the proof of that's in the pudding. I can find my position, they can't. Therefore, that's pretty good evidence that my model's the correct one, and theirs isn't. Plus, I actually know what I'm doing with this. They don't have the first clue. So, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by and visiting with me. Now, we'll have some more work on the sextant in the future. There's a lot of mathematics involved in doing this. I showed you basically once, given the geographic position and the sextant altitude of the star, you can easily draw circles of equal altitude on Google Earth and find your position. Now, there's a lot more mathematics in this, and the devil's certainly in the details. We'll go into that a little bit more in the future, but this is really all you need right now to be able to solve a sextant challenge. So, take care, make sure you hit that like and subscribe, and thank you again for all my subscribers and my Patreons and the members of my channel. Now, because of your support, I'm able to obtain cool instruments and experiments for the channel, one of which is this right here, which is a fully functional astrolabe. We're going to have a lot of fun with this in the near future, and 2022 is going to be the year of the astrolabe and the armillary sphere. Two objects that are 2,200 years old that rely on a globular Earth in order to function, and they do indeed function. We'll start off by building them, and then we'll learn how to use them. So until then, take care, and I'll see you again soon.